Really?
That'll be backwards.
Yeah.
It'll correct itself. Okay. All right. Hey everyone. Get seated. We'll get things going. All right, hey everyone, my name's Alex. I'm the organizer for the meetup. Thank you for coming out today. Just always like to kind of start off with telling a little bit about Data Nerds. Data Nerds is a meetup focused on the data, education and working with data. We meet weekly to work on projects together, and we meet monthly like this to have conversations around data. This month we have Alexander Poon coming to talk about solving the cold start NLP problem. I'd like to also introduce our sponsors. We have Zrol Group here sponsoring the coffee and bagels, and Belmont providing us this great space to meet. So without further ado, I'll let Zrol take over.
I don't have a whole lot prepared, so just appreciate you guys letting us come and provide food for you. We specialize basically just in technology recruiting. We do have an accounting and finance division as well, but we stick on the IT side, infrastructure, PMs, VAs, QAs, .NET, all that stuff. So we always have those kind of positions available. If you're looking, definitely reach out to us. We can at least let you know what's in the market. And if you're just curious, whether you want to know if salary ranges are out there for jobs or kind of what the next skill set people are starting to look for, that's always something you can reach out to us as well, because we're obviously seeing all the new jobs that are out there. So I appreciate it, guys.
Thank you. Thank you.
All right, go ahead. All right. Morning. And thanks for coming out and listening to me talk about this. So let's all get on the same page. Sorry. Let's all get on the same page. What am I talking about? So NLP means we're doing data science with text. Broadly speaking, we're trying to make sense of large volumes of text data. And cold start means that we want to do text classification. So typically when we're doing classification in machine learning, we have a bunch of units of text, and we want to assign labels to them. So the way this usually works is we have a data set of, in this case, like emails, and we have like correct labels associated with each of these units of text. So this example, like a canonical example, is classifying emails as spam or not spam based on the word content. So what usually happens is I have a data set, split it, and then live happily ever after. But the cold start problem refers to when you don't have labeled data, meaning that I have all these units of text, but I don't have like correct canonical class labels associated with each of my units. So then I can't do that thing where I build a machine learning model because I don't have the truth, these base truth labels. So this is the problem that I'm going to be talking about. I've been sort of wrestling with it for about like 6 months or something related to a project that I've been working on. And I'm going to talk about that, how I solved that towards the end. So I'm going to break this down into 2 cases and talk about like the solutions for each of the 2 that, the way that I've been thinking about it. So case 1 is what you're looking for. So let's talk through some examples. So I went to this talk at Strata Data Conference in March, and there was a couple of data scientists from Lockheed Martin. And what they wanted to do was, Lockheed Martin is this giant defense contractor. They have lots and lots of suppliers. So what they wanted to do was search through like business news for any sort of mention of mergers and acquisitions related to any of the companies that they buy things from. So in this case, like UTC is United Technologies, and they're buying some other company for $23 billion, something like that. So here's another example. One of the tutorials for the package that I'm going to talk about, one of the examples is like finding associations between chemicals and diseases in the biomedical literature. So I guess like lithium carbonate is a chemical in this case, and tricuspid valve regurgitation is something you don't want to have happen to you. So they're trying to scan the medical literature, medical literature, large volumes of this without having to, read all the individual stuff and try to find associations between like chemicals and diseases. So here's another one, looking for spam in YouTube comments. That's a pretty like canonical example as well. There's like a data set out there. It's kind of like ImageNet or, Boston Data Housing. It's just this like publicly available data set that people can go and, try to do their best at like identifying spam out of these YouTube comments. I'll talk about this some more in a bit as well. So here's the idea behind the approach to this first problem, where we sort of have a general sense of what we're looking for. The idea is we're going to use like rules and heuristics to create some data labels. So in the first case, where we were looking for mergers and acquisition news in business news, the folks at Lockheed Martin, the approach that they took was that they used the SPACY annotator. I don't know if y'all are familiar, but like SPACY is, I'm a big fan of it. Like it does lots of things. It annotates your text, like you feed it some text, it annotates it for you, meaning like it identifies parts of speech like nouns, verbs, etc. It identifies like dependencies. So, if this is a verb, like this is the noun that's like doing the verb. This is the thing that the verb is happening to, like the direct object. So identifies like dependencies in that way. It does name entity recognition, so names of like people, places, companies, that kind of thing. So the approach that these folks at Lockheed Martin took was that they applied, they fed all this text to the SPACY annotator, and they were looking for patterns. Like, then this is going to be the theme, like we're looking for patterns, and so we can sort of try to encode that in like code, and try to like have our code identify those patterns. So they're looking for a pattern of the form company, and then anything with like a lemma of merge or acquire. So like merge, merges, merged, etc. And then the name of another company. And they also like, since they have that dependency parse, they can like rely on the fact that this company is doing, they can identify the fact that this company is doing merging or acquiring, and this company is like the target of the merger or the acquisition. So that's the idea here. So in the chemicals and disease example, we can do something similar. We're looking for patterns of the form where we mention a chemical, the word cause, and then a disease. So enter the Snorkel package by this NLP research group called Hazy Research. So the idea is that you write labeling functions to formalize these rules and heuristics that we're coming up with. So I'll show you examples of what that looks like in a little bit. So what they call this is like weak supervision. So when you have at the beginning, like where I showed you, where we have perfectly labeled data with like correct canonical labels, that's called like a supervised learning problem. When we don't have any sort of class labels, that's like a supervised problem. So this is like calling this weak supervision because we're like somewhere in between. We're going to come up with some labels for our units, but they're not like perfectly correct because we're relying on these heuristics and shorthand as opposed to like, meticulously going through each document and coming up with labels. And so the thing that's really nice about Snorkel is that it integrates seamlessly with like Pandas, SPACY, Scikit-learn, Keras, like all the things that you're, NLTK, all the things that you're already using in your natural language processing workflow. So here's an example. So in the tutorial, they want to encode this rule. Like they want to tag comments as spam if they tell you to check out something, like check out my video, check out my channel. So this is like a few examples in that YouTube comments data set. And so this is what the code looks like. We import the labeling function, and then we write we use that decorator, and we write these functions that say like return spam if I see the word check in my text, or if I see the word checkout in my text. So these functions, like I mentioned, like they just rely on sort of all the tools that we're really familiar with as data scientists. So it just returns NumPy arrays of, in this case, 1, 0, 1. So 1 is spam, 0 not spam. -1 is like abstain. So you can tell your function to either, if you don't find the thing, you can tell it not, you can tell it no. You can assign it the negative case, or you can assign it like the abstain case, which says like we're not making a judgment one way or another, because like, check and check out doesn't cover every instance of spam that we're going to want to identify. So we don't want to just say like, if it doesn't have the word check or check out, then we're going to make the judgment that this is not spam. Like we can assign it the abstain case. So NumPy arrays 1, 0, 1. You can do like multi-class classification. So if we're looking for more than just 2 classes, you just get your array is like 2, 3, 4 corresponding to the any more like class labels that you come up with. So that was like a pretty simple one. We're just like scanning the text, looking for certain keywords. You can get more, like a bunch more sophisticated. I already mentioned spacey, so you can leverage that in writing a labeling function. So here, like these people have decided that a ham comment, like ham meaning not spam, comment is one that is like if it mentions a person and if they're short. So like I guess like someone went through and looked over a few examples and decided like that's a rule I want to encode. So I mentioned that like we can leverage like spacey does the named entity recognition, so it can identify like, oh, there's the name of a person in this comment, and you can leverage that in writing these labeling functions. So we're looking for somewhere where an entity is a person, and the length of this document is less than 20 words. So the key here is that like you want to label, when you're doing this sort of weak supervision, you want to label both of your cases. You want to identify examples of spam and not spam, like, because otherwise if you don't, like if you only identify one of the cases, then in the end, like you can't do classification, right? If all of your labels are just the same, if there's only one value to your labels, you can't do text classification. You need examples of both your positive and your negative case. So the workflow here is that like you come up with a bunch of these heuristics, these rules, and you write a bunch of labeling functions corresponding to each of those. And then you can combine their outputs to produce a single canonical, like this is what I'm deciding via my weak supervision or data labeling process. Like I'm going to assign like a final single class output. So like one simple way to do this is like if you were to write a bunch of labeling functions in this case, you could just take like a majority vote, like more of my, among all my functions, five functions say that this is a piece of spam. This, 2 of them says it's not. So then I'm just going to take the majority vote. That's like the simple way to do it. But like there's this label model thing that does this in like a much more sophisticated way, and the details of which I think I definitely need to read some more about. But it does this in a much more sophisticated way. It like checks how correlated your functions, your like labeling functions are with one another. So like check and check out are going to be like generally like pretty correlated. So you don't want something like that to like have an you don't want to overvalue like your labeling functions that are like super correlated with one another. It also takes into account like what they call coverage. So the like proportion of your documents that you are either assigning a label to or not. So it like takes into account like various aspects of all your labeling functions and tries to come up with like probabilities in a much more sophisticated way than just like a majority vote. Pause there. Any questions?
Everything you've done has been in Python?
Yes.
Sure.
Yes. Okay. So that was case 1. So case 2 is one where like you don't know precisely what you're looking for. So you might wonder like, how is that possible? So I'll give you like a couple examples from that I've sort of had experience with. So my day job is at the Tennessee Department of Education, and every year the Department of Education administers the Tennessee Educator Survey. So we send out a survey to all the teachers, principals, et cetera, in all the public schools in the state. And we give them sort of like agree, disagree questions. But at the very end, we give them this like open response question, which is like, is there anything you want to communicate to the Tennessee Department of Education? So then, teachers can write whatever they want. And so, we know that there are certain themes that generally emerge, like teachers often talk about compensation or like funding related to education, or there's too much standardized testing. Like we know that there's certain themes that appear year over year, but the research team who administers this survey over at the department came to myself and another data scientist and said, is there something that teachers are talking about in large proportions that we might not be able to? An example, we want to find, but we're not exactly sure what we're looking for. So here's example 2, and this is the problem that I've been working on for some time, is trying to make sense of legislation that's coming out of our legislature just down the road downtown. So the idea is what I've been trying to do is do search and recommendation for legislation, which basically means depending on where you are, where you live, what sorts of policy matters that you're interested in. I want to be able to identify pieces of legislation that might be of interest to you. And so, that answer is going to be different for everyone in this room. So the idea is that I've been trying to find as many features as possible that might find as many ways of classifying legislation in a way that I could use that to do, search and recommendation for legislation. So, excuse me. So one problem, and this is the thing that I've been sort of wrestling with for some time, is educate, the bills where I get my data from, it assigns a policy area to each piece of legislation. So education, for instance, but education is a really big policy area. Something 1/8 of the legislation that comes out of our legislature relates to education. And so in my data, I have something like 3,000 pieces of education bills. And so to tell someone hey, you're interested in education, go read 3,000 pieces of legislation doesn't feel all that useful. So I've been trying to come up with a way to find more specific groupings of bills among this education legislation. Again, kind of vaguely knowing what I'm looking for, but kind of wanting to do this organically, find organic groupings of meaningfully similar bills. So I'm going to talk about that example basically for the rest of my time. So the idea here, excuse me, the idea here is we're going to partition our documents into groups based on presence of similar words. So put on our thinking face. And so here's what you sort of have to convince yourself is true for this to work, is that okay, for if there's a group of bills that relate to higher education, there's going to be certain words that are key to that fact, right? They're going to mention colleges and universities, tuition, semester, credit hour, campuses, et cetera. There's certain words that are key indicators that my bill is going to be about this certain topic. And the same is true of something like school choice. So if there's a topic that's school choice, then it's going to mention things like charter schools, vouchers, virtual schools, home schools, that kind of thing. So what we're going to do is topic modeling. So topic modeling is the thing that we're doing. Latent Dirichlet allocation is, as best I can tell, one of the more popular ways to do topic modeling. So let's go through what exactly latent Dirichlet allocation is. So Dirichlet is a statistical distribution. And this is sort of what it looks like. It's this is the case where we have 3 topics, let's say, and we want to assign all of our bills to one of these 3 topics. So each of these points I get in this case would represent one document, and in the top corner here, we would be saying that this document belongs purely to topic 0 and not to anything else. And so if you're like in the middle of this triangle, let's say, like you would be saying it belongs, like it pertains a little bit to each of the 3 documents. So this is a Dirichlet distribution. It has this parameter alpha, which is relevant, and there's this really nice illustration that hopefully this works. So like for different values of alpha, like that distribution looks different. So higher values of alpha means that more of your documents live in the middle of this triangle. So when you're doing this latent Dirichlet allocation, you sort of have to decide like what you believe to be true beforehand. Like, do my documents generally pertain to a small number of topics, or do they sort of pertain to a large, a little bit of everything? And like that's going to be, one of those things. Some of that's going to be true. Like some documents are just going to be that pertain to one specific thing, and some are going to, cover a variety of topics. But, the hint here is that if we want to partition documents into like small, meaningful categories, it's probably helpful for them to be like, these documents to be really distinct from one another. So the general case is that like we take something that looks much more like the, much more like this than the one where everything sort of lives in the middle of this. So this is the three topic case. Of course, you can generalize to any number of topics.
Is the number of topics a parameter going in, or are you specifying that?
You specify that, and I'll talk about like how to decide on that. So the latent part means like we assume that there's some underlying distribution of topics across documents, and the allocation is like this algorithm is going to assign a distribution of topics for each document according to this Dirichlet distribution. Yeah.
Does it also decide what the topics are itself?
It doesn't. So I'll talk about that at the end, but like basically you have to go and interpret. So here's how like the sort of workflow goes. We feed it like a bag of words model. So, each of our documents we represent as like, this document has 1 of this word, 0 of this word, 2 of this word, etc. So it's just like word counts. And this is like a really big, a really wide matrix, right? So like all the words that possibly appear in all of my legislation, like, it's that number of columns wide. And I have some, like I mentioned, like 3,000 or so documents. So this is a big matrix. And LDA represents, like the output of LDA is 2 things. So one is that it represents each document as a combination of topics. So for instance, my document might be like 50% of this topic, 20% of this topic, and like this, you interpret these as percentages, so it allocates, like how much, like in what percentage each document belongs to each of my whatever number of topics I decide I'm gonna allocate to. And the other thing is a distribution of topics over words. So it tells me like what words are associated with each topic, and that's where like the interpretation piece comes in. I go look at all the words that are highly associated with topic 1, 2, etc., and then I can, like as a human being, like interpret what the meaning of that topic is. Cool. So there's 3 parameters of interest. One is number of topics. So you sort of decide that beforehand, and you feed that to the algorithm. You can, of course, like trial and error, iterate over various numbers of topics. And I'll talk about in a second, like how to decide on what the optimal number is. And then 2, it's this alpha parameter, which corresponds to like that alpha in the Dirichlet distribution. So basically that alpha controls like how many topics a document can fall under. Does it tend to represent a small number of topics, or does it tend to represent like a large, does it tend to be distributed across a large number of topics. And so I mentioned like we probably want like a smaller number of topics because that makes it easier to interpret. Like if every document it represents like a little bit of each topic, then we don't get that much like value add from like partitioning these documents into these topics. So I think like a default that a rule of thumb that I've heard is alpha is like 1 over the number of topics that you decide you want. And then eta is like similar. It controls like how many words are associated with each document. So depending on your like experience with data science, this might remind you of a couple of things. So one is clustering with like quantitative data. In our case, like what I'm doing is partitioning all of these text documents into groups that sort of look like one another. That sounds an awful lot like clustering with like other quantitative data. Words matrix, it was many thousands of columns wide, and then I'm gonna take that and represent it. Instead, I'm gonna represent each document as like some number of topics that's way smaller than that thousands of columns wide. And so that like the idea behind dimensionality reduction is like it makes something easier to like sort of think about, like it's easier to wrap your head around. Let's say like 20 topics associated with each document as opposed to thousands and thousands of columns that carry a lot of information, but it's like hard to wrap your head around.
Yeah, it's like an autoencoder. You're encoding it, although autoencoder, the output of that is not very interpretable, but it's taking that information and distilling it down into
Yeah, fair. So there's a bunch of there's a handful of implementations. I use the one in GenSim. So this is what the code looks like. I decided before, through trial and error, through evaluation, that I want 20 topics. Then I use the LDA model in GenSim. I feed it vague words, the number of topics that I decided I want. So I mentioned that like you feed it an alpha and an eta, those two parameters. You can also ask it to like figure it out for you. So you can just do this auto thing. And this is like a stochastic algorithm. So if you like run it again, you don't get exactly the same result. So I like also pass it a random seed. So a couple ways to evaluate how good your topic model is. One is with this statistic called coherence. So basically what it's getting at, so you get a coherence, like a coherence score per topic. And so what this is sort of getting at is like all of the, among all the like words associated with the documents associated with each topic, like how distinct are those words from all the other groups of words. So it's a score between like 0 and 1. And so you can look at like a coherence score per topic. So you can see like, I've got like a 0.76 here. That's like as high as I've seen anywhere. So it seems like that group of, that topic, the documents that are in that group, which is like, that's ideal, right? That's what we're trying to do with this topic modeling. We're trying to get distinct groupings of documents that have like, words that are associated with one another. And so like the like single canonical coherence score is just like the average of all of my individual topic coherence scores.
Is there like a rule of thumb when evaluating coherence? Because imagine as you increase the amount of topics, your probably overall coherence. Am I thinking of that intuitively right? Or
so you asked about like how do you figure out the number of topics. You can use coherence to sort of decide on that. Okay. This doesn't correspond to my use case. I just pulled this off a blog somewhere, but basically you like try a variety of numbers of topics, and then you plot your coherence score, and like the rule of thumb is like where it starts to flatten out is sort of what you decide that.
You can't say like 0.4 means good.
Yeah, that's right.
Like more is better. More is definitely better.
Yeah.
Okay.
Having them is great, but if you have, if it's comments, for the restaurants, there's so many different varieties of that you just hope that it's sometimes it could be 0.3 looks good, where it's obvious. Like I've done this with employee satisfaction data, and coherence goes up high because everybody complains about pay, benefits, not enough time. It goes the same stuff over and over again.
Okay.
So it always comes back to the same one, so your coherence goes way up with employee satisfaction versus comments at a restaurant kind of thing.
Right, which will be all over the
Yeah,
place.
because it worked where if you had that employee or the
Educator.
I mean that I would say you're going to see a lot of groupings pretty quickly with that. If you do it.
I personally did not work on that a ton, so I don't know. Can't say too much about that. But I can refer you to I can point you to the person who worked on it if that's interesting. So this is a way to, like that question of how do I know how many topics to use? Like here's a way to like objectively sort of evaluate that and decide on an optimal value. That's like wherever this curve starts to flatten out.
Always seems like that's the case. You look for the elbow.
Yeah. So there's also this thing called LDA viz, like you're visualizing an LDA model. I think I'm gonna fiddle around with my computer here, show this like interactively. So this is another way of evaluating a topic model. So this is what the output looks like. See if I can. Okay, that doesn't really help. But you're visualizing this topic model basically, and each of these circles over here on the left side represents one topic. Like the size of the circle tells you like how many documents are associated with that topic. So big circles means like we think that there are lots of documents associated with a particular topic. So what we're looking for here is that these circles don't overlap with each other. So, but it's a distance map, so it's sort of getting at like how close my topics are to one another. So, like we were mentioning, we want our topics to be hopefully like as distinct from one another as possible. So we're looking for as much non-overlap as possible among these circles on the left. And if you see like you have a bunch of circles sitting on top of each other, that might actually like be an indication that you have too many topics, and all those circles that are sitting on top of one another ought to be combined into one topic. Let's see.
What is that?
The thing on the right.
No, just how did.
It's
Where's that from?
Pile. It's so LDA viz was implemented originally in R, and this is the Python port to it. So that's like the evaluation part. So the second part, another component to this is like actually interpreting what this means. So we have these topics these documents that get put into these groups. We got to decide for ourselves like what these topics actually mean. So one way to do that is with keywords. So remember that we broke that big matrix into two different matrices. We want to look at what words in that second matrix are like highly associated with each topic, so that we can interpret what exactly these topics mean. So you can use the show topic method, associated with an LDA model. And so any guesses as to like what we're talking about here?
Funding for schools.
Yeah, exactly. So like raising money for schools. This isn't really helpful, but I create this data frame where I have like the coherence score associated with each topic, number of bills, those keywords, and then like the bill that's like most associated with each.
Do you choose the number of keywords before you fit the model, so it just throws out the bottom whatever, or does it make weights for all the words you've got and you've just chosen the top 10 or whatever?
The show topic method, I think, only shows 10, but that ADA parameter that I mentioned, like that's what controls like how many words are associated with each topic. Okay. So the other way to like interpret topics is to like look at the most representative documents. So the ones that have like the ones that are most concentrated in each document, each topic. So the way we do that is like we can sort of like take our LDA model and extract the proportion that each document falls into each topic. So for my first document, it's like 93% associated with topic 10. I think it doesn't show any values that are less than like 1% or 5%, I forget. So that's the key, like this first document is very highly associated with topic 10. The second one, it's like, it's dispersed a little bit across various topics. So then like the other, what I do is like extract all these values, extract these things for these like topic proportions for all of my documents, put that in a data frame. And then, I can like sort on, sort high to low along each dimension, and then like look at in my case, like the builds that are the most representative of each topic. And then that's a way for me to like, interpret, assign like a human meaningful label to those documents. So like LDA viz, like there was that other half of the graph that I didn't show you, but it's sort of does something similar. It gives you like most relevant terms, and it does more than 10. So that's potentially helpful. I think we were looking at, doesn't matter. So like pick one, like pick a topic, and what it's getting at on the right is like, the red part is how frequently this word shows up in this document, or in this topic. And then the blue is like how frequently it shows up in my corpus overall. So you can mess around with this like lambda parameter over here. So as you like lower this lambda parameter, it increasingly shows you words that are more uniquely associated with this topic, as opposed to like up here. It shows you like words that appear in this topic very frequently, but it doesn't like sort of filter down for words, for sort of like unique words that are more uniquely associated, or more like only associated with my particular topic. And you get more than 10 words, so potentially that's helpful for interpretation. There we go. So what I do is like, I assign labels to documents. The last part is like actually assigning the labels to the documents. Like I do that where topics like substantially fall under one topic. So this is like not very scientific, but I sort of like looked at, where, at what point of, these topic percentages, at what point do I feel like, below this threshold, I'm not really getting topics that I think, or documents that I think should be associated with this topic. And I decided on like 0.4. So I assigned these baseline labels, like for topic 1, if a bill has a percentage of is like associated 0.4 or more with this topic, I'm going to assign it some label. So, pause for questions.
Did you eventually use this as like an input into your model as like additional feature, or?
Not sure what I'm doing with this yet.
I'm not sure. Okay. Like, okay. So you
basically like I think it'd be helpful for people to be able to like query on these. So,
search. You're
yeah,
trying to
exactly.
Search quality.
Exactly.
Okay, I got you.
Yeah. So that was maybe a lot of information. So let's recap. Like, it's 2 cases that I talked about. The first is like this data programming approach where we write labeling functions that encode these rules or heuristics. And this is helpful, like if you know what you're looking for and there are like relatively few classes, feels harder to have to write like multiple labeling functions times lots and lots of different classes. So I kind of think of like these 2 solutions that I talked about as like covering very different, maybe polar opposite use cases. And then we combine information across those labeling functions to produce like class probabilities. So in both of these cases, right, you'll notice that I did like, it's not like there's sort of some fuzziness associated with it. Like in the first case, we get class probabilities. In the second case, like, topic, documents are can be associated with multiple like topics. So this is sort of like, these are both sort of like probabilistic or, not like fuzzy classification techniques. So the second case, we use topic modeling. We're partitioning documents into relatively homogeneous groups based on the words that they contain. And this was helpful like when we don't exactly know what we're looking for. So like we can find clusters of documents that are similar, that look like one another, that we didn't necessarily know were there, and we can handle like sort of arbitrarily many, as many classes as exist in our corpus. So we can evaluate it with this coherence statistic and the LDA viz. We can interpret it with keywords and the most representative documents. And then the last part of this workflow is like actually assigning the labels to our documents. And that's all I have. Questions, comments?
So a question about your labeling function.
Yeah.
So, and the first example I saw was the acquisition. So let's say alpha acquired beta.
Yep.
Alpha acquired by beta. Is if you created a labeling function where you had to define acquired and acquired by mean very different things. I mean, can you create a truth that will overly influence kind of your learning model, or how does that work?
I think you'd have to like play around, like be very careful with like the logic there. I think like at a minimum, that's two labeling functions, acquire and acquired by.
Right.
And probably in the acquired by function, you have to like account for not,
Right.
or the other way around. In the acquire function, you want to like acquire and not acquired by, and then your second function is acquired by if you want to like sort of make the judgment that those two things are distinct.
For another example, John promised to leave Mary. John promised Mary to leave. So it's really about word order. So word frequencies are identical.
Yeah.
In the second example, but word order is relevant.
And I guess you could use order or like dependence, like depending on how good the like spaCy annotator is, like you can sort of leverage it to see who's doing the leaving or the acquiring.
Can you create a label for like a multi-word expression or phrase?
Yeah, like basically anything you can, any idea you can express in code, like you can write a labeling function to correspond to that.
You're leaning on spaCy to do some of that for you,
Yeah.
is that right?
Yep, I like spaCy a lot.
Have you done any performance tests for spaCy versus just NLTK? I mean, I like spaCy.
For what purpose?
Just time to compute.
Uh,
I mean, so I like spaCy, but
it takes a
NLTK because spaCy, for what I was trying to do, was just really slow.
Yeah, the annotation part is really slow. Maybe helpful is like depending on what aspects of spaCy you're trying to leverage. Like you can disable, like the, exactly, and that can like potentially speed up. But I think the point is right, is that like spaCy takes time.
Right. But for what you're doing, it wouldn't matter if you use spaCy or NLTK or anything else for that tokenization.
Not for the tokenization. If you're doing like the entity recognition, that's where like you can just do that and disable all the other parts, and then not so bad essentially.
How for the topic modeling scenario that you mentioned, how many words on average are in like the
quite a few.
And how does that, or can you comment on how that might affect the performance?
I think
of the data?
it's like a give and take, because when you have more words, there's like more signal potentially as to like what this document is about, but there's probably also a lot more like chaff that you have to like, you know, when you're doing like NLP, like part of the, you know, pre-processing, like data cleaning process is like getting rid of like stop words and so forth. So like the more text you have, like the more, like I think the better you have to be at sort of getting rid of everything that doesn't carry any meaning, but you also get like more signal about what, in the topic modeling case, like what this document is about. So I think it's like both, like having longer documents is both potentially beneficial, but you also have to do more work to sort of drill down on what in your, you know, what words in your document are like meaningful.
So I've been trying to do something similar.
Okay.
But, you know, I'm working with documents that have, on average, I'd say 5 to 10 words.
Okay.
And
Yeah, that's tough.
yeah, it's been pretty tricky
Yeah.
trying to extract anything.
You know, man, what are you working with that type of
It's a Venmo data set. So
Okay.
a lot of the transactions
Oh, yeah.
And it's just, I mean, there's just so much gibberish in those
Yeah.
comments.
Good luck with that. There's some semblance of signal. I'm just curious. Do you do anything with the emojis? Like, does that work?
So I try to decode those.
Okay.
As best as I can, but
Gotcha.
yeah, that's,
I mean, you can treat emojis as their own token, like as a token, and
Okay.
yeah, you can do
Is
that.
it represented as like the word when you're processing it?
Yeah.
Okay.
So I try to convert the actual thing to the word, but those are actually less meaningful sometimes.
Yeah, I know whenever I send money on Venmo, I just give the floppy disk for any
See? And Venmo really encourages the use of emoji when you make a comment on the transaction, so it's like, yeah.
All the noise.
I
don't think I've realistically commented on what I paid for ever. So,
Thought it would be interesting.
that's an interesting problem.
It's interesting, but it was pretty interesting.
To mention my use case I did over the summer, which was in employee satisfaction surveys. They had negative comments and they had positive comments. It's two separate ones. So I did two different ones. And who I was doing it for usually uses graduate students to manually label it into 28 buckets. 28 buckets. First I'm like, what are you doing? 28 buckets. But so could you imagine trying to take 14,000 comments and putting it into 28 buckets? That's what these poor grad students had to do. And so they hired them for 3 straight weeks, 2 at a time. So you're talking 40 times 100, that's 240 hours. They paid these 2 students to sit there and do it. And I gave them, using LDA, I did it, you know, and gave it to them. And I'm like, I guarantee mine are better, because how could any human put each one distinctly into your 28 buckets? And I said, first of all, your 20 buckets is down. Let's get it down. I got it down to about 12 meaningful ones. And again, so 5 hours of work compared to 240 hours of work. And I felt mine was better. And they, I was like, so I want you to pay me the same amount. And anyways, so I think it does a good job of taking some of that down. I mean, could you imagine doing all that?
No.
Annually? That's what we used to do, right? That's what grad students are for. That's what we use them for.
I'm kind of new to, I'm more on the analytics side of things, and I'm new to data science, but would you take a random sample of these documents and yourself kind of cross-reference just to check your model, like to see how, you know what I mean?
Yeah,
Subjectively, you could think it goes in this direction, the document, and somebody else could read it and go, well, I think it affects these things a little bit, you know? You give a random sample and just cross-reference it, see how strong it's correlated, like subjectively with what you think that this Word document has in it.
yeah, I've done a lot of, like, related to my legislation thing, I've done a lot of just like, you know, reading. But I'm not doing anything scientific on my end in the way
Yeah.
that, you know.
It's like a way to evaluate performance, right?
On the ham versus spam idea, you usually create your training set that's a lot of times manually done.
Yeah, yeah.
Or, you have to create that somehow, and then you're using that to help calculate.
So you still sometimes need the interns to do 400 hours of work, to kind of give you an idea of what you're getting, right?
And they still, even though they were gonna use me, and they felt comfortable that my results would be fine, they had the money, the budget for these students, and they're like, wouldn't this be a cool little project to see manual versus the LDA version of it, and to see how it, how it would be. And I tried to do 28 buckets at first, and that's what I started at. And it's like, why do you start with that number? Because that's what they told me to. And then you just keep going down because I kept seeing too much overlap over and over again. But yeah, the idea is to do a little bit of the manual stuff. But if you do it on 10% of the data, well, that saves you 90% of your time. And so it's always goes back to that.
Yeah, so like unspoken is that like if you don't have labeled data, you can just pay a bunch of graduates to do it. So that's solution 3, I guess.
I was thinking you can maybe use that to do quality control on manually labeled data.
Yeah, you can like
If you find associated over the whole body of text, and then look for outliers which have been labeled as whatever, but are very dissimilar to the topics you've assigned to it.
Yeah, so like going back to, this part, I came up with 20 topics, but there's always like outliers, oddball documents that don't really fit anywhere. So I think like even if you do this and it works really nicely, like you might still have to do some like looking at all your documents that didn't really fit nicely anywhere and decide like, oh, it should have gone here, but like the LDA didn't identify that, or like this like truly doesn't fit anywhere. So I actually had to do a bunch of that, like with the documents that don't get assigned a baseline label in this way.
Have you ever looked into the works of that
Yeah. And for what?
topic model?
For count. No, I haven't I haven't really thought about like using like this, like semantic representations of words to solve this. If you have ideas,
No,
I'm happy to chat about them. Yeah.
About it.
And there's something also called Doc2Vec. So in this instance, I would think Doc2Vec would be, because Word2Vec is individual words.
Okay.
Where essentially what's happened is, Google trained Word2Vec to create this vector space of and relationships between different words. So the whole man to king, woman is to queen. Of course, anyone who looks into it, there's also gender biases and racial biases in it. So it's always careful when you're coaching Word2Vec to understand that it is a representation of kind of society's biases. So I always put that as the disclaimer. Doc2Vec is an instance where they tried doing that with an entire document. And Google even has this new thing where you can pass in a sentence and it encodes it. I'm blanking on it. Just something I read the other day. But even if doing Doc2Vec, you would be encoding it. I actually don't know anything about Doc2Vec, but I can't speak to that. I'm not sure how that would play in.
I only played with Doc2Vec like this much, and it didn't work for my use case, so
Okay.
I haven't explored it very much since then.
Gotcha.
Cool, thank you.
Yeah.
Thank you.
Looks like everyone needs to take like 4 bagels with them.
Yes. Thank you, Alex, for speaking. Result had to leave, but thanks to them for bringing in the bagels, and thank you everyone for coming out today.
Thank you. I ran an NMF from some data for the first time. Maybe that's